Hi everybody, my name is Overtime and I want to present to you a work done by myself and my colleague Dan Swissa under the supervision of our advisor Professor Brafman. We will talk about some background and motivation regarding robotics and AI planning, overview existing systems, talk about the gaps we found, our contribution, an experiment video, and an illustrative example. So let's start with a short recap on AI planning and POMDPs. POMDP is a way to model the world and to describe a planning problem. In POMDPs, the agent is unaware of the current state of the world. It maintains a belief state, which is a distribution over states, to reflect his belief on what is the current state. It can apply actions, and these actions they probabilistically change the state of the world. So we have a transition function which is for every state we have when we apply an action, we have a probability to traverse to every one of the possible states. When we apply an action, the environment changes its states, and we receive an observation. And by this observation, we can update our belief state, and we also receive a reward. Now, in AI planning, we want to solve this planning problem, and to solve this planning problems mean that we want to find a policy which is a selection, a policy for selecting actions conditioned on the belief state that maximize the total accumulated expected reward. And we think that POMDPs are very appropriate for robotics. Why? Because physical agents they usually have probabilistic actions, and also robots they have a partial, possibly noisy view of the world with their sensors. So how can we describe a POMDP? If you want an AI solver to solve it, we need to describe it. There are two ways to do it. One of them is an exhaustive description. This is suitable for very small problems. For example, if I have a problem with 10 Boolean state variables, then straight away the number of possible states, my state space is around 1000, and then my transition function for a particular action, it will be a table of around 1 million cells. So this is hard to describe this way, although there are formats that describe it in this way. So what do people usually do? They use action description languages, ADLs. And we have RDDL, which is an ADL for POMDPs. And in this example, we see how we can compactly describe the transition function of a domain. RDDL is very expressive. We can in this domain we have a problem. We have a 9-cell grid, and each cell can be burning or not, and we can see in this image we can see a code of RDDL describing the next value of each state variable of the burning, if a cell is burning or not, dependent on the XY. And we can see that we can describe if-else conditions and also mathematical expressions, and we can also describe sampling from a Bernoulli distribution or other distributions to describe probabilistic changes in the state. So this is a very expressive language that can compactly describe this wildfire domain that can be found in the RDDL tutorial webpage. We have a claim that we say that current ADLs, they are not expressive enough, and we are always looking at robotic problems. So why are they not expressive enough? Because even though RDDL, for example, is a very expressive language, they don't have all of the control structure you can find in a programming language. For example, you don't have while loops, so I can describe everything. Let's say, for example, I want to sample from a certain distribution a cell in the grid, and if this cell meets a certain condition, then I want to say that this cell is burning, and then I want to stop sampling cells. So I just want to turn to make one cell which is burning, and this is something I can't do with RDDL. I can link if-else expressions, which will be okay, pretty big, but okay when I have 9 cells, but it's not practical for a larger grid. So this is one thing. And the other thing, another example is that in this domain the fire can spread to neighbors. So they exhaustively describe all the possible neighbors, which is also pretty hard to describe when we have large problems. But more than that, let's say that in my problem cell neighboring changes dynamically in my environment, and this is something I can describe in RDDL, so it's not expressive enough. And real world problems, they require all the tools to describe. The second problem is the abstraction gap. What's the abstraction gap? Let's say that I want to activate the put out action, which is inside this domain. Then after the agent select a certain cell to put it out, then I will need to write additional code that stitches the selected actions to activating a robot code. So I have a certain gap between the abstract model used for planning and low-level robot code. And also the other way around, because in POMDPs we receive observation from the environment, so I need a way to translate low-level code variable values into an observation that the planner can reason with. So I have this gap to both ways. What we advise, we saw that probabilistic programming languages, they can compactly describe complex probabilistic models, and we think that an ADL powered with a general purpose programming language is required. These languages, and we specifically talk about C++, which is a mature language. It is used to solve real-world engineering problems, and it's very expressive. It has a large set of implemented code to construct and manipulate data structures, and both of the examples I gave, they can easily be solved using and described using C++. About the abstraction gap, we will also talk about this further on. So let's talk about the state of affairs today. This information was given to us by interviewing engineers from 2 large companies working on autonomous robots. So how do they develop the robot? First of all, they develop a set of robot skills, basic skills like navigation, object detection, arm manipulations, things like that. And then they have they handwrite a script, and this script is for scheduling the robot skills, and it's for scheduling the robot skills and to achieve a high-level goal. And this is not simple for them. Why? Because physical agents, they have probabilistic actions, so it's hard to write such a script. And also, as we said, sensing is partial and noisy, so it's hard to write. And even after you wrote a script and you manage to handle these challenges, once the environment change, like in this example, the basket that you're putting all the toys, if now it's become 2 baskets, then you need to rewrite this script. Or if you upgraded the code, then you need to change the script. So why don't they use AI planning? We will describe our problem using AI planning. If something changes, we will just change the problem description, and AI planning will do the rest. The reason is because there is a significant integration effort And this integration effort, it comes from two reasons. One is the gap between low-level robotic code to the abstract model used in AI planning, and the second is because the ADLs, they are not expressive enough. So let's see the available systems. First of all, we have ROS-Plan. ROS-Plan was the first general purpose AI planning system that integrated with robotic execution. It supports PDDL, which is a deterministic model for planning. So if something happens unexpectedly, then you need to perform replanning, and this can cause repetitive behavior. They also support RDDL, but not fully. They don't support partially observable domain or noisy sensing. They require significant integration. We experimented with this system, so it's a good system, but it has its drawbacks. There is the CLIPS Executive, which is it has goal reasoning. It has a predefined plan in the form of a goal tree, and each goal is pursued using a PDDL planner. And by the result of executing the plan for this goal, then by this result they know how to update the goal tree and to pursue the appropriate goal. And we have the skill-based architecture, and they propose a formal language specifying robotic skills. So this is something more specific for robotics, and they auto-generate code that assists the integration phase, but the user still need to write some code. And also they support PDDL, which is as said only for deterministic actions. So the gaps we found, we saw that current ADLs are not expressive enough for real world robotic problems, and available systems, they require significant integration effort. Also current systems, most of them don't support probabilistic planning, and all of them don't support partially and noisy sensing of the world. And also we think that a solution shouldn't be tightly bound to any specific robotic framework like ROS-Plan, which is very tightly bound to ROS. What we introduce. So our contribution is the AOS. The AOS is a complete methodology and tools to automatically bridge basic robot skills and AI planning. The basic skills will be documenting using our GSDL generative skill documentation language. This is our action description language that uses the power of C++, so it's very expressive. And we also have an environment file to describe the state variables and robot objectives, and to answer the problem of the gap between robot code and the planning model. Then we have the abstraction mapping to document this gap. So every skill is documented using a JSDL and an AM file, and we have one environment file for the objectives. The AOS is a plug-and-play solution, which means that user only need to document their code, and once they are using the system, everything is integrated automatically. The planner is running the skills and it's activating them, so the user doesn't need to write any code inside the AOS, so nothing except documenting is skill and objectives. Let's overview the system architecture quickly. We have the AOS Web API. This is how the user interacts with the system using HTTP request. Once it requests to integrate his documented code, then the Web API auto-generate some components inside the system. We have the planning engine, which is responsible to decide what is the best next skill to schedule. The unifying layer is used for communication and storing statistics. The functional layer middleware, this is the section that actually activates the selected skills on the robot framework. The functional layer, this is the robot framework, and after it activates a skill code, then it listens to public data that is published on the framework, and also it receives the response, the return response of the code, and from all of this it calculates an observation which the planning engine can reason with. Now the planning engine itself, we use PROMCP, but we are not limited to PROMCP, but still we are using sampling based techniques, and the reason we take the documentation of the skill behavior, and we place it inside the planning engine. Why? Because in this algorithm the sampling rate is very important, and if we were to use a generic code, the same generic code for all of the domains, then it's a lot slower. It's slower than auto-generating code, and we experimented versus RDDL Sim, which is an open source code used for the international probabilistic planning competition, and we saw that our code can be 40 times faster than this generic code. Okay, so let's look at some experiments. What we see here is the Panda robot, and we are doing here a tic-tac-toe experiment, human versus robot. What we did here, we implemented two basic skills. One, the robot can mark a circle in each of the cells, and the other one, the robot can detect changes in the board. We documented them, and we document inside the environment file that the desired state is to win the tic-tac-toe game, and it's undesired to lose. And we see that the robot is acting in a sensible way. The main purpose of this experiment is to show how we can easily integrate basic skills using our documentation, and we saw that it works smoothly. This is the armadillo robot. We have one in the lab, and this experiment was done on a gazebo simulation. In this experiment, we have probabilistic actions with noisy sensing. The peak action was designed to be probabilistic. It can succeed or not, and also it returns noisy observation. So we documented the pick skill, the navigation skill, and the serve to person skill, and we saw that the system is using them in a sensible way. Let's look at an illustrative example. So it's just to get the look and feel of our system. We have a robot with a single navigation skill, and it needs to navigate between 3 known locations, and this skill has a 10% chance of failing, but 80% only on 80% of the times it fails, it returns that it failed. So it has noisy sensing. Let's start from the bottom. This is our abstraction mapping file, and in here we can see that there are 2 possible observations when we are activating the skill. It could return success or failed, and this is conditioned on local variables. Local variables, it's a concept we defined, and these local variables, they are only existing per activation of the skill. And we can condition them. This can be written. This is written in Python, so you have the flexibility of using Python. And in here we define the goal reached, which listens to a topic. A topic in ROS, it's public information that processes inside the robotic framework they publish. And we can define a function on the input. In this case, if goal reached is published, then this variable receives true, and then you can build a condition that it returns the success observation. And also we describe how to actually activate the robot skill, and this is designed for ROS, so how to activate a ROS service, which is a skill, and you can use parameters which are also can be local variables taken also from the abstract model. We have the environment file to describe the goals, to visit the 3 location, and where we have our GSDL to describe the high-level behavior of the skill. So you can describe here that this skill, that the robot discrete location, it can, when you're activating a navigation, it can lose its orientation with a chance of 10%. We are sampling for Bernoulli. Otherwise, it reaches its destination. And in here, we describe the observation model, which is noisy, and this is how it is described. And you can also describe the cost using the reward saved word. You can describe the cost of activating the skill. So we talked about our contribution, the system, which is our system, and our ADL, which is powered by C++, and our way of doing to bridge between low-level code and AI planning models. For future work, we want to do a user study on the AOS, and we want to implement a user development environment for the system, to add multi-agent support, to add anomaly detection, and also to improve the documentation given by the user based on the robot experience. Thank you very much.